Hi, my name is Haiti Garcia, and this is my video presentation for lab number 1 on constant velocity for Intro to Physics at Georgia Tech. So just a little overview of what I'm going to talk about. I'm going to first give an introduction to the experiment, and then I'm going to give an overview on the observational model, and then an overview on the computational model, and then I'm going to compare both of these two models and how they're similar and how they're different. And then I'm going to conclude using some physics principles and answer a couple of questions. So for today's lab, we're observing an object that's in constant velocity, constant motion. We're going to observe it in a physical experiment, which in my case, I used a ping pong ball and wooden floors. We're also going to model this experiment theoretically through a Java code, and then we're going to compare these two models and understand the meaning of an object that's in perfect constant velocity, including but not limiting the effect of forces and acceleration on a system. So the main physics ideas that we're going to talk about in this lab are the position and velocity update formulas. So the velocity is the final velocity equals the initial velocity plus the net force divided by the mass times the change in time. And the position update formula would be the final position equals the initial position plus the average velocity times the change in time. And the average velocity in this case would just be constant because it's in constant motion. So the final and the initial would both equal. And then Newton's first law, we're going to cover that as well, which basically says that any object that's in constant motion or at rest will remain in motion or at rest unless it's acted upon by any exterior forces. So in this case, the system would just be the ball, and the surroundings are the floor, my hand, anything else that's not including the ball, for our case. And then the second, Newton's second law would just be also called the momentum principle, which says that the net force equals the change in momentum divided by change in time, which also equals to the mass times the change in velocity divided by the change in time, which also just equals the mass times acceleration. And we're also going to talk about the idea of net force. So for my observational model, I used the tracker software to track my physical ball, a recording of my experiment, and compute data from the experiment. So as you can see on the right, the position and time graph shows a somewhat linear graph. As you can see, it kind of has like a little bit of like acceleration. As you can see, that it kind of curves and bows out, and this is due to the fact that a lot of forces were actually present during the observational model, just because of like the fact that there is friction and air resistance. All of this could account for the little bit of acceleration that we see in the graph. Despite this, we're trying to get this to be constant motion, and it just can't because it has too many exterior forces going on. So as for the computational model, we used a Java code that I just changed up. So for example, the initial position vector, I updated it since at time 0, the ball was not in position 0, it had already moved a little bit on the x-axis. So I went ahead and updated that initial condition, and then the initial velocity I just calculated by doing the change in position over change in time. The delta t I changed to 0.033, which is the increment of seconds that the time was stepping by. And then the last bit of edits that I did was in the while loop, and I just edited the velocity and position update formulas. And also the net force was set equal to 0 because that's what you want for constant motion. So as you can see, the observational model had a net force despite the intended conditions, explaining the resulting acceleration, and the computational model is more straight because it did not take into account any outside forces. So for my final questions, what if the axes were oriented? If the axes were flipped, the graph would instead illustrate the same data but as a negative slope, since the ball would be rolling in the negative direction. And it's not possible to say how many pushes or pulls are added together to give the zero net force, because the ball is presumed to be in constant motion, meaning there is no net force. And that's all. Thank you for listening.